Good afternoon, everyone. So what I'll try to do today is tell you about where nanosciences and nanomaterials could be useful in the area of information technology. Co-authors, collaborators from a bunch of different organizations. I'll sort of give you a perspective of where things are headed. Some of my own research has begun here with some of my postdoctoral scientists in the group, and I'll show you some of these initial results and also talk to you about where we are headed. So please feel free to interrupt me if you have any questions. We'll keep this informal. Okay, so in 1662, Robert Boyle, many consider him the father of chemistry, came up with this wish list of 24 things that he wished to see. Okay, and in this list of 24 items, a large fraction belonged to the field of material science, and I've highlighted some of those in yellow. And if you look through this list, it's a very interesting list, many of which we have attained today, like the art of flying, number 3, and many of which we haven't, like number 11, which says the making of glass malleable. Okay, and there's many interesting things over here. Varnishes perfumable by rubbing, a perpetual light, which I think with solid state lighting we are functionally, I think, very close to meeting this requirement. But of all of this list, there are a few things that are missing here. Can anyone take guesses? What's missing here that should have been apparent to Boyle even at that time? Any guesses? So, brains? Yeah, that would be one. And related to brains, information technology, computing, it's not listed here at all. Another area which I find interesting is that Boyle talks about making a better ship somewhere here. He talks about a ship to sail with all winds and a ship not to be sunk. He talks about the art of flying. But he doesn't say anything about better land transportation. He doesn't even ask for a better horse carriage. Okay. So that was the other thing that missed out. But information technology is the item that he missed, and that of course changed our world since then and will be the subject of my talk. So if you look at the chart at the top left, this is taken from Ray Kurzweil's book. But and I like to show this because it tells you that the cost of computing has gone down by over 15 orders of magnitude in the last 100 years or so, roughly. And with microelectronics coming in, it's gone down by about 6 or 7 orders of magnitude. Okay? And this has happened because of our ability to miniaturize semiconductor devices. I pick another quote from a philosopher, Gaston Bachelard, who says that the cleverer I am at miniaturizing the world, the better I possess it. And of course, he was referring to the case where he was locked up in jail at one point, and he used to draw these train stations and a picture of a little train, and he used to imagine himself going out to freedom by getting into this picture of the train on the wall that he drew, and he miniaturized this whole thing. And that's what he meant in his quote. I felt that is very appropriate for us as well, in the sense that the idea of scaling a technology, making things cheaper, faster, smaller, all at the same time, makes us better possess our world as well. Okay. But the technology that has gotten us there, which we sort of in condensed form call as Moore's Law, is going to end within the next decade or so. Right? And I'll go over it a bit. But basically, transistors used to scale in density, and they would scale in performance. And we are already off of the performance scaling trends. Okay, a smaller transistor isn't better anymore. The benefit we get today is from density scaling. But even that is going to come to an end, primarily because the cost to build a transistor is saturating. It's the same. In the past, one transistor used to cost less than making one transistor from the previous generation, and that has saturated. So now, if you're doubling your transistor count in the chip, the price of the chip keeps increasing. And from a business point of view, that is going to put a lot of pressure. And then workloads are changing due to big data. We often seek qualitative answers instead of precise, scientific numbers. We want to, say, for instance, which is a better picture out of a bunch of pictures, that sort of thing. And so while microelectronics has continuously improved, basic computing architecture has not changed in the past 60 or 70 years. And there's a lot of interest in that changing as well, and new types of non-von Neumannian logic or architectural approaches coming in. Okay? So, which brings me to the next chart. If I sort of look at the future, I see this as a three-branch tree. Okay? At the bottom is business as usual, and I'll talk about that in a moment, and that's silicon technology, and you keep enhancing it with silicon CMOS, and you keep enhancing it with different types of add-ons. The second branch is the one that is, I think, the least developed, at least conceptually. It's this whole area of low-power devices, spintronics, tunneling devices, things like that. These devices can, in principle, produce certain advantages, but they don't fit into a silicon scheme of things because there is no good architecture or circuit to go along with it. And then there is the third branch on top that digresses completely from standard CMOS, von Neumannian architectures and goes to things like neuromorphic computing and quantum computing. And this is an area where both DOE and Argonne is putting a pretty large emphasis on, and this is going to be the future of materials, circuits, device research, as I see it. And in my talk today, I will focus quite a bit on some of the work that we're doing on materials and devices for neuromorphic applications. Okay. So in this talk, I'll first spend a few minutes just describing the conventional computing roadmap, what's happened, where are things headed. Then I'll talk a bit about neuromorphic materials and devices. And then I'll talk about something that I also consider as part of future information processing. You can think of it as distributed computing, where you have sensors scattered all over the place, and it gathers information, and it provides intelligence at a sort of system or geographical level. And I'll talk about some of the things I've been involved with and some of the things that we plan to do over here in the future. Okay. So let me start with conventional computing. So till about 1990, microelectronics was driven by bipolar technologies, bipolar transistors. And the power consumed by bipolar transistors became increasingly high. And at one point, it was untenable. At that point, CMOS came in. There's a side story to that. This was the time Lou Gerstner came to IBM as its new CEO, and he made the bet at that time to switch from bipolar technology to CMOS technology. There were two big mainframe manufacturers at that time, IBM and Hitachi. Hitachi stayed on bipolar. When the first generation of CMOS-driven mainframes came out, they actually performed worse than bipolars. That was anticipated. But this is where they used Moore's law to scale and project that in a couple of years it's going to beat bipolar. That actually happened, and Hitachi essentially went out of business. So that was one of the big things that Lou Gerstner ended up doing. And this is little known, but he had a big influence on the way CMOS technology itself was shaped. Then from between 1990 to 2005, was the era of classical device scaling. You took a device and every 2 years, you shrunk it by 70%, essentially using better lithography tools. Okay? And when you shrunk it, you needed less voltage to run it. The device was faster. You increased the density by a factor of 2. Okay? And that continued till what's known as the 19 nanometer node, which was 2005. And then in 2005, we needed to do new things to the transistor. So here is a transistor. There's a source, a drain, there's an insulator. You put some image charge on top of the electrode over there. And you put some charge on top of the electrode, you get image charge here, and you can modulate the flow of current, right? That's a simple description of a transistor. But basically, the planar geometry became a difficult one to work with. There were things called short channel effects. This oxide material, which was silicon dioxide, needed to be replaced. And it got replaced with something called hafnium oxide. That happened in 2010. But doing all these patches, replacing part of the silicon with germanium so that you got silicon germanium transistors. And actually at APS and CNM, there was a lot of work on imaging strain in silicon germanium transistors that played a role in this. So by 2010, you continued staying on Moore's law by doing all of these fixes. Okay? And that's what we're doing today. And then today we are somewhere around 14 nanometer node. This transistor is no longer planar. It's called a fin. That's called a FinFET. But pretty much by the time we hit 7 or 8 nanometer node, it'll be a case of this far and no further. And we will now make our improvements not by shrinking the transistor anymore, but by doing other things in the architecture. Okay? So this is another interesting poem I came across, which I thought I'd put it up there. So John Updike, as many of you know, is a very famous, person in the literature world. He was inspired by an article on material science in the Scientific American in 1969, and then he wrote this poem. And the poem shows a surprising grasp of physics and chemistry, and a lot of the things he writes about, this was in 1971, directly relevant to the development of microelectronics. And he talks about, within the cracked and dislocated real, non-stoichiometric crystals dominate, stray atoms sully and precipitate, strange holes, excitons wander loose because of dangling bonds. And, this is a guy who had a liberal arts degree. Having this grasp of science was very impressive to me. But anyway, coming back to the scaling, so a lot of the future in the traditional CMOS world is going to go to the package level, system level, communications level of the computer, right? About a third of the energy is spent in processing. About roughly a third is spent in what's called I/O, or communicating the data, and about a third goes towards memory. So there's going to be new things. There's work on looking at carbon nanotubes to replace silicon for low voltage operation. Non-volatile memory is coming up big. That would replace DRAM. Flash is an example of non-volatile memory. We can afford flash in our laptops today, but it's still way too expensive to put in mainframes and servers. So one of the drives is to make flash or flash equivalent memory that is cheap. Optical links will come in through what's called silicon photonics and on-chip power conversion using magnetic inductors, gallium nitride. ARPA-E is funding this heavily. So these are the kinds of things that you will see coming through in the next 5 to 10 years, primarily driven by industry. This is all very sort of applied development type of work. Okay? So if we now go to the way architectures have evolved, and I am no architecture expert, so this is what I gather just talking to my microarchitecture colleagues, is that in the standard way a computer is configured, the memory is kept away from the processor, right? There is one processor, and if you want to run something, you get data from the memory, and then you pick what you need, you throw everything away, and then you run a computation. So you end up getting what's called a memory bottleneck, and it's also a very inefficient process because you keep shuttling data back and forth. And for data compute intensive operations, this becomes a problem. So then they start placing processors closer to the memory. So if there's a baby processor here, it can take some of the memory, identify what is important, and then send that to the main processor. And then there are pros and cons of this. One of the cons being that you have so many processors. Now you got to keep track in terms of clocking as to what's going on. Two processors can't hit the same memory address at the same time, stuff like that. Right? But if you take this kind of approach to its natural consequence, right, this is where you come to what we think would be new forms of computing, such as neuromorphic or quantum computing, where there is no clear distinction between memory and logic. And in many ways, the processing or the logic happens through the interaction of the signal processing pathways, right? And that's where we would like to head. And then the question is, what are the materials, what are the circuits, what are the architectures that we would use for this? So I showed you this chart before, this three-branch tree. Let me look at it a slightly different way, in a more sort of technology-focused way, right? Again, 3 branches here, and this time the lower branch is still the middle branch here is still conventional computing. I talked about Moore's law scaling. When that goes off, there'll be silicon photonics, 3-dimensional integration, more memory coming closer to the processor. Okay? Then there's the quantum branch, and that's a train that's already sort of leaving the station. And then there is this branch that we call neuromorphic memory, neuromorphic computing. Now, software neural networks are already here, widely used. Everybody here in this room inadvertently uses neural network driven processing throughout the day. Okay? So this is happening in software. So then the question is, can you put in some hardware to make it faster? And that's happening, or beginning to happen, at a CMOS level, and companies are investing in that. And they're doing this through field programmable gate arrays, general processing units, things like that. And here are a few examples. IBM has the TrueNOT chip. Google just came out with something that's called a tensor processing unit that basically multiplies vectors in an analog fashion with some loss of precision. But if you take this to its natural consequence, this is where I believe the world of research in neuromorphic lies, where you look at materials, devices, and approaches that now drift away from silicon, which is not really the right material to use for this type of application. Where here in this world, you try to get your inspiration from biological systems and pick materials and material systems and physics ideas and concepts that are more in tune with that. So let me now compare a biological system and information processing in it with a silicon CMOS process, right? So in silicon microelectronics, the switching speeds are much faster, gigahertz versus kilohertz. But the voltages are about a factor of 10 higher as well. Typically, silicon chip will run at about 1 volt. If I look at, your neuron, it fires at about 100 millivolts or so. On-off ratio, there's a difference. There's a massive difference in fan-out. Fan-out means if you have one wire coming in, how many wires can it split out into? And in conventional microelectronics, you're limited to about 3 or 4. Okay? And that comes from Kirchhoff's law. If I have a current coming in a wire, if I have to have it fan out into 1,000 wires, I have to have a real thick wire coming in, right? And you can bypass that in biological systems. That allows you huge fan out. It's a big difference, right? Allows you a lot more complexity in your circuitry. Coming hand in hand with that is the fact that in microelectronics, the power sources are remote. In biological systems, you get power from the bath around you through the transport of ions that sets up a Nernst voltage, and this voltage pulse then skims in what's called saltatory conduction. Charge carriers are free carriers in microelectronics, much faster. Multiple ions in biological systems offers much more functionality. Okay? But given the richness of biological systems, there are a lot of materials, particularly I believe this family of oxides, mixed oxides, oxychalcogenides, that can have the richness in their structure, microstructure, to offer you this type of functionality. So you want to look at materials where you can write a state, or in other words, modify the materials at very low energies and very low voltages, okay? And you can try to do that by controlling the architectures of defects, perhaps configurations in surfaces, things like that. This is like a wide open field, okay? And this is where a lot of basic science can be done. Going in hand with that, we have to be able to figure out how to deal with variability. When something runs at very low voltage, things are variable. One device will behave a little different from the other one. If I take a silicon chip, it has 1 billion transistors in it, and each transistor works within about 30 millivolts of the other one for a turn-on voltage. If you lowered the operating voltage from 1 volt to 100 millivolts, just from thermal fluctuations alone, you will not get that variability. So you have to think of architectures and approaches that can embrace this variability. Right? Materials for signal transduction, and then the physics of learning, which I'll come to in a moment, which is, again, wide open. So let me go back to a neural network and a neuromorphic system, and then talk a bit about the kinds of materials and devices we can use to make synapses and neurons. Shown on the top left is a very simple sort of neural network. I'm just learning about these things myself. But basically, a neuron's principle is that it will take signals coming into it, and then it will integrate that signal, and when that signal crosses a certain threshold, the neuron will fire, and that's called an integrate and fire operation, or at least that is our sort of very simple interpretation of this neuron. Now, when the signal is coming down a path from a previous neuron, then there is a strength of this path that can be used to modulate or control the signal. And this strength is controlled by essentially the synapse. So I can think of the synapse as something that has a variable resistance, for instance, that I can set. And so when I tune a neural network, I am basically adjusting the weights of these resistances so that I can change the integrate and fire response of the neuron. And then when I have a whole bunch of this, I have a bunch of inputs, I have an output. This could be, for instance, a number recognition system where I have a number, break it up into 72 pixels, a value of each pixel, and I can have 9 output neurons here, numbers 0 to 9, and I can tune it to do a number recognition system. So, how can we do this in hardware, okay, using new materials and devices and circuits, but with energy consumptions that are maybe 100 to 1,000 times less than silicon implementations? That, I think, is the challenge. So here is another aspect of these neuromorphic systems, is in the way you adjust the weights of these synapses. Today it is done in a very sort of standard statistical manner. In biological systems, it happens probably in a much more integrated fashion. There is no understanding today as to how that happens biologically. So even if today we can make these synapses and neurons, say in silicon, and in future we'll make it using other materials, but we will still run the neural network using standard software algorithms. So this is another big opportunity as to figure out how the learning process occurs. Okay? But typically when a neuron fires for a while, then the signal decays, and there is a refractory period for which it does not fire. Okay? So it integrates the charge, fires, the signal decays, and it rests for a while, and then it's ready to integrate charge again. Just remember that. So now the making a synapse and a neuron. So I spoke about the neuron here. Today, you can make a neuron using silicon CMOS. It consists of a charge integrator. Okay? It consists of a waveform generator that sends the signal out. And it consists of a little circuit that stops integrating while the waveform is being generated. So it's a rather complicated circuit. And the question is, are there materials that we can use that can demonstrate these sort of functions of a neuron, but use it using new types of materials? And then in the synapse, can we make something whose weight can be adjusted? And if you think about it, and if you use resistance as your parameter, then you can use what's called an analog memory, something where, say, the resistance varies as a function of voltage. So I can always write in a resistance, it stays, and I can erase that resistance by putting a voltage, say, in the opposite direction. So I could use a material where I'm altering its microstructure somewhat. So let me give you an example of some of the work we've started on looking at materials and devices for synapses and neurons, okay? Now, the evolution of synapses came from work on non-volatile memories. As you know, DRAM is volatile. So as DRAM becomes, 64 gigabytes in size, about 40% of the time the DRAM is connected, is in communication with the processor, but 40% of that time is used just for refreshing the DRAM. So that's not very practical. So there's a lot of interest in looking at things that will replace DRAM but are non-volatile. So magnetic random access memory, MRAM is an example. RRAM is a sort of slower version of DRAM. It's called resistive RAM. So people have looked at phase change materials as things that could be future non-volatile memories. And the first thing electrical engineers sort of did when they wanted to make these synapses is start using some of these sort of phase change materials or resistive RAM, or it's called chemical bridge RAM materials, for use as synapses by having them display some type of hysteresis in their resistance behavior versus voltage. Now, all of these materials, so if you take phase change material, for instance, germanium antimony telluride, it's the standard material that was developed for compact disk surfaces. Okay? But in a phase change material configuration, you heat it, melt it, and you cool it either slowly or fast to get an amorphous or a crystalline state. And the two states have two different resistances, and that's how you have your analog memory. In a resistive RAM, you have a material with two types of metal electrodes, and you put a bias. There's some oxygen vacancy redistribution, and its resistance changes. Chemical bridge RAM is similar, but it's considered to be a little electrochemical cell. You have something like copper with a dielectric and a bottom inert electrode. You apply a voltage. The copper forms a conducting filament. You can erase that filament by offering a reverse voltage, but that's your memory state, right? So there are various approaches, all sort of on the same principle that you're changing the microstructure of some medium and therefore changing its resistance. Now, a little bit of description, of this issue of variability. Okay, this is a big issue. We tend to sort of hide it under the table as we keep pushing on low voltage technologies. But if you use a simple concept of a resistive state being changed, in this case, let us say, by a filamentary formation of a line of vacancies, or it could be, let's say, some solute atoms that form a filamentary line. If we assume that this is diffusion limited, okay, then one can do a sort of very simple back of the envelope calculation to show that the variability in the resistance of this device is going to be inversely proportional to the energy that you need to impart to the device to change its state. So which means the lower the voltage, the higher the variability. It's also obviously varies as the square root of the area of the device. So the smaller the device, the higher the variability. Okay? So this is a very important thing that we need to take care of. We want a device that works at a couple of 100 millivolts, but we have to work with architecture researchers to figure out how we will deal with its variability. So let me give you a couple of examples of work. The first one is an example of synaptic behavior in a device, and this is work that Sushant Sonde, a postdoctoral scientist and colleague of mine, has been driving. So in this case, we have a platinum electrode, an inert hafnium oxide dielectric, and a copper electrode on top. Copper is a fast diffusing element. The idea is that if you apply a field, this copper somehow forms some kind of filament and its resistive state changes. You can make the device, it's a standard processing that can be done in a clean room, and then you test these devices using what are called crossbar structures. Okay. Shown here is a TEM image of this type of a device, copper, hafnium oxide, platinum, and thanks to Yuzi for doing the TEM of this work. Now we've been looking at these devices and they show a rich, very interesting set of behaviors. Okay. So if you look at the, if as fabricated, these devices work at a very high voltage. They show the hysteresis that you expect. There's a lot of variation from device to device simply because the individual devices are rather big over here. If you anneal them, then you change the microstructure and you allow them to then turn on at much lower voltages. The data is a lot cleaner, as you can see. The current changes as a function of voltage. And then when you anneal them further, this is an oxide, but it behaves almost like a semiconductor with a much lower band gap, which is also very interesting. And we are doing some electron microscopy work to try to figure this out. A few more interesting things. When we make the hafnium oxide thinner, 4 nanometers, we see much lower voltage operation at about 0.4 volts, which is very exciting to us because, usually most of these devices will work much higher at about a volt or above. The second interesting thing we see is that when we run it at 20 degree Kelvin, we still see switching behavior. Which is surprising because at 20 Kelvin, if this is a diffusion thermally activated process, then you would not expect this type of thing to happen. If we do a TEM analysis on it again, clearly there is a lot of copper in the hafnium oxide, and so that is indeed modulating the conductivity. But a lot of this behavior is not understood at this time, and we are trying to figure this out, but the promise remains that it can have low voltage operation. There's this big question of how is this diffusion happening? It doesn't seem to be really thermally activated. We are trying to figure out right now if there is any self-heating going on at 20 Kelvin, but right now we don't think so. A second example, and this is work now Jerome Lin, who is another postdoctoral associate colleague of mine here, is focusing on. And this is now trying to make an artificial neuron, but using a metal to insulator material. Right? So if you take something like vanadium oxide, many of you are familiar with it, it has a thermal metal to insulator transition that if the temperature exceeds 70 degrees C or something like that, its resistance drops. If you grow good vanadium oxide, its resistance can drop by about 5 orders of magnitude. So the question is, can you use that as an integrate and fire neuron? So Jerome has been modeling these structures. And this is a very interesting device because it is a combined electrical thermal capacitance type device. So when you pass current through this device, it heats up. When it heats up, at one point its resistance drops. When its resistance drops, the current increases. That's the firing of the device. Okay, and then when it cools down, its resistance goes up again, and then there's the refractory period is defined by the amount of time it takes to cool down. And the integrate and fire comes from the accumulation of the pulses and the heating of the material. So this can all be modeled in a tedious but conceptually straightforward way. And in the graphs over here, I will ask you to just focus on the one on the right, that when you fire it under certain conditions, and basically we see that it will change its resistive state. If you do what's called a quasi-static simulation, where you increase its voltage slowly in steps and then back down again, you will get a hysteresis in its turn on and its turn off, okay? And the hysteresis simply comes about because it has two different states in resistance from when it's heating up to after it's heated up, and the power dissipation is then different because the power is V squared over R. And R is different in this arm and this arm. So there's a lot of interesting, rich phenomena here that can be used in a compact device model if you look at it from a purely electrical engineering point of view. Okay? And this is what Jerome is trying to do. So, you can think of two ways of having a neuron. Okay? One is you use voltage as an input, and this structure over here that looks like a Frank Lloyd Wright structure is what we call the insulator to metal transition resistance. And if you can input through voltage pulses, it can act like a neuron the way I just described. The other way is to have a current source give inputs in the voltage and have a capacitor over here that sort of acts like the integrator. As you keep passing charge here, the voltage across this capacitor builds up till at one point it discharges through this resistor as the resistance also heats up. And when you do that, you run through the simulations, we expect neuron-like integrate and fire behavior. So we spent actually a couple of months simulating all of this, and Jerome is right now in the process of trying to build these neurons. Anil has been, another of my colleagues, has been growing the vanadium oxide layers, and we're actually in the process of building these neurons, and hopefully in another few weeks or so we will have these results. Okay? But from these simulations, you can make a simple artificial neuron and replace this whole little silicon CMOS circuit, and yet be able to demonstrate the three critical things the neuron needs to demonstrate: integrate and fire, the fact that there's a refractory period, and that there's a certain profile of the firing. Okay. I talked about this. This is the part where you look at the way biological circuits and our microelectronic circuits are interconnected. There is almost zero work in this field. And this is another area rich in opportunities, is trying to figure out how to deliver power in a different way. And I talked to you about Kirchhoff's law and the fact that having a remote power supply limits us in silicon microelectronics, as opposed to a biological system where I'm basically getting power through a Nernst voltage potential difference, through movement of ions, and then this voltage skims across. Okay? So I am not delivering current flowing because of a potential gradient between one end of the wire to the other, which limits me in microelectronics. So this is something to think about for the future. I will change gears a little bit now, and how am I doing on time? Okay. And talk to you now a little bit about sensor networks. I think there's a lot of opportunity for looking at nanomaterials for making new types of sensors. Most of our efforts on semiconductors, oxides for nanomaterials has been devoted towards making better computers, better logic systems, etc. Very, very little work in the sensor area. But I think this is the big opportunity. There is some work in the making sensors using optical techniques, but very little using electronic techniques. Right? Now, sensors today have to be part of a larger network and a larger system. We can't just focus on making a sensor, but it has to be part of the system that I'm showing here. The way to think about it is to have a network of cheap sensors that you can screw in and out like a light bulb in a system. The data is uploaded to the cloud using low power wireless technologies. In the cloud, you can take the data, and very interestingly, you can run them through physics models to get new information about a system. This is something new. This is something not too many people do, and this is an enormous opportunity for physicists. And I'll show you a few examples that I've been involved with, and then push the data down to smartphones, etc., to provide some meaningful information. Right? And this sort of system is what's called the cyber physical system. This, I think, can be a calling card for applications of nanotechnology. Here is one example. This is a project I was involved with when I was at IBM with Gallo wineries. The idea here was to use satellite data. It is free. Landsat satellite data, you can do almost optical spectroscopy. You get 11 different wavelengths twice a month, free. You can download it, and you can do whatever you like. In this case, we use the red and the green wavelength data to make chlorophyll maps of a vineyard. This vineyard was pixelated in terms of the water delivery. And using the chlorophyll maps, we actually calculated the amount of water needed. And so we delivered more water to places that were browner, less water to places that already had too much water. Okay? And to cut a long story short, this experiment was done over 2 growing seasons, and there's a 10 to 20% improvement in both yield as well as water efficiency, which means amount of water used for a kilogram of grape that you grow, or something like that. And this is just using free satellite data. Now imagine the benefits that you could have in something like agriculture if you were to measure other things. So the 2 most important things are soil moisture and dissolved nitrates. Today you can measure them, but these sensing systems cost between $1,000 to $2,500. You need these things every 10 meters or so they're unaffordable even for grapes, for wines, okay? Let alone other crops. So that is a challenge, making very cheap sensors, okay? And so some of the things that we're involved in is in looking at trying to measure soil moisture and soil nitrates. We're starting off with some approaches for soil moisture. A second example I will show you is again using satellite data, in this case infrared data, and this is a case of using simple physics models to get a lot of information. So if you take infrared images, again from Landsat, you can then back out and calculate and estimate industrial productions from large plants and factories. Okay? So it's a very simple sort of, maybe even advanced undergraduate level problem where you are measuring the response from a satellite, and it's measuring light coming out of the plant which is operating, and you make the assumption that if the plant is producing more equipment, more things, it's producing more heat. And the reflected lights of the sun, you can do a simple calculation, and you can try, and you have to measure things like wind speed, the amount of convection that's going on. And this allows you to then estimate the amount of heat that this thing that you're trying to measure is producing. This is some work that I did with a couple of colleagues. And here is an example. Go to Google Maps. This is an Alcoa aluminum smelting plant. Smelting plants produce a lot of energy. So this is the picture of the plant. These are 2 bands in the infrared, somewhere around 1.7 microns and about 2.1 microns. Okay? And when you take this image, you need to calibrate on the emissivity somewhere. Thankfully, all of these aluminum plants have a big stack of coal. Okay? So you identify where the coal is, you take your emissivity number off of that, okay, because you know the emissivity of coal. And you can calculate the temperature, and then from that, you can estimate the amount of heat coming out. And we did that for plants in the Middle East and in the US and so on. You can find out that in the Middle East, they built a huge plant, but they're only using 25% of it because only a small portion of it is really lit up. Here's another example. This is a power plant. One of my colleagues who worked on this was from China, so he went back to a plant that he was familiar with. This is a power plant in China. And we did the same type of analysis using, 10 to 11 micron data. And, we did an estimated heat output. And then if we went back to the web, we found that actually we could figure out when this plant was shut down because there was a dip in the data. Okay. There's increasing amounts of satellite data coming out. Landsat comes twice a month. There's a European satellite with better resolution that's just started the past few months. Next few years, there's going to be a huge amount of data like this coming out. Google, Amazon, they are they are basically archiving and creating huge repositories of this data set of satellites. There's tremendous opportunity for physicists here. You have a spectroscope right there, okay? There's so many clever things one can think about, which the big data people have no idea about, okay? So that's an opportunity. And this is just satellite data. Imagine if you're measuring stuff cheaply, locally, using a sensor. So much stuff you can do. Okay? And here's a third example. This is for water. Okay? So this is the Ganga River in India. Okay? It's one of the most grossly polluted rivers in the world. I'll give you a simple number. There's something called fecal coliform that you monitor. And if you're in a lake in Vermont, if you have more than 400 fecal coliform colony-forming units per 100 milliliters, you're not allowed to swim in that lake. In the Ganga, the number varies from 1,000 to 1,000,000. Okay? So that's how much more it is. This is a huge problem. So one of the things I was involved in, and which we've switched the river, but I have a proposal in to do this in India, is to monitor these things using the sort of sensor network that I just showed you. And part of this research is then in trying to figure out simple ways of measuring water quality, okay, such as fecal coliform and biochemical oxygen demand. Today, there are no good sensors, and when there are, it takes days to make the measurement, and they cost at least $1,000, which makes it unaffordable. So in terms of sensor challenges, you look at the areas of water and agriculture, which I feel are the two big areas to hit. As I mentioned earlier, soil moisture is big, dissolved nitrates are big, and if you can measure fecal coliform and biochemical oxygen demand, and these will really change our approaches in monitoring different industries and fields. Okay? So this is something that we've just started working on. Zhou Feng has joined. He's going to be working on these sensors. Also at the university, using the campus as a lab concept, we're setting up a little base station and antenna. There's an Internet of Things wireless company called Sigfox. They specialize in very low data rate wireless systems. We are putting this antenna and base station on top of Eckert Research Lab Center building, and we're going to be embedding the campus with sensors for soil and water to have sort of this type of network that I described to you. And hopefully in a year or so, we will have some really good results coming out of this activity. And so I will conclude my talk with just, description of what I feel is the ultimate sensing network. There's this vine in Chile called the boquilla vine, and it has this unique property. This vine grows on trees, and it mimics the shape of the leaves of that tree. And here are 3 examples. This is the paper, if you can look it up. But just look at this. In this case, it's done a good job. Over here, it's tried to do a good job. In the third tree, it's again done a good job. Now, this vine obviously cannot see, but it is measuring something and adapting to something. And this, in my view, is probably, the most primitive form of intelligence, which a distributed sensor network and an information system tends towards. And this would sort of be the ultimate goal of a sensing system. With that, I'm going to conclude my talk.
Questions for Supratik? So let me start off with one. So the refractory period of a neuron, is there an understanding of what the purpose of that is, or is that just a bug rather than a feature?
I probably don't know enough about this field yet. I'm still learning. But I think there is, actually I don't know. I don't know the answer to that clearly. From, our viewpoint of this thing probably doesn't make sense because it slows the speed down of the interaction. But from a biological perspective, I actually don't know.
So, other questions, please? Michael.
Hi, very nice talk. I was thinking with the sort of artificial neuron that you're trying to make, if it could be instructive to use microfluidics to make an artificial neuron.
That's a very good point, and I've sort of thought about it where you could use water pressure building up and opening up a membrane. Was that sort of what you had in mind?
Well, normally, neurons will be conducting ions across membranes.
Yeah, yeah.
If you had different channels going into a cell, then you could send different kinds of signals down the channels.
I think, we've sort of focused on electrical approaches simply because, that's our prejudice, that's the world we're used to. But I think a fluid-based system makes sense to try because I think one could have a lot of advantages there. Even in things like adjusting the weights, I think there could be benefits there. I have been thinking about this, but, it's a good idea. I think there was a question there. Was there a question at the back? No. Maybe
Back
not.
over here.
I was actually curious about some of these different commercial implementations that you were talking about, tensor processing, the True North chip, NeuroGrid, and Spinnaker. Are they all taking the same approach, or are there different approaches to
There are
those
different approaches doing different things. So some that I'm familiar with, the IBM True North that tries to build a neural network using silicon. So it means that it builds, its neuron is a bunch of SRAM cells and a whole different circuit. So the chip is huge. So these are not the most direct way to make these things, not the most elegant way to make these things. But because silicon is around, we know what to do with it. That's what people do. If you look at Google's tensor processing unit, that is basically a matrix multiplier. So if you have a crossbar array with elements in between whose resistance can be changed, you can work it out very simply that if you send current down these parallel rows, then along the column, you basically get the summation of this. And you can use that to multiply tensors or vectors. I believe that's what Google's tensor processing unit is. So they're all different types of approaches. I think the natural progression of this will be that you would use, general processing units, then you would go to sort of reduced precision general processing units, then you'd start sticking in little analog components to what will still be a digital processor. And from there, maybe go on to doing fully analog. So for instance, if you have a processing unit that's digital, but you can do matrix multiplication in analog fashion very quickly, you may have a little processing unit on the side where you go back and forth doing that analog processing. Just in the same way that, video accelerators came, whatever it was, 15 years ago. It was something that was set aside from the main processor. Analog accelerators, I think, will come in. But that will all still be silicon. Okay. Marius?
Thank you. So you mentioned quantum computing, but did not elaborate much. Can you tell us where do you see that going and what role the lab can play?
Yeah, so if you look at quantum computing or quantum information, so there's quantum communication. So I will not talk about that. But if you look at the computing piece, then you can look at digital quantum computing, which requires error correction. I think that, Google and IBM are the leaders. It is well developed. That train has left the station. If you look at analog quantum computing, that is where you try to sort of mimic some kind of Hamiltonian by making another Hamiltonian out of all these qubits. And I don't really understand this a whole lot. But nobody's satisfactorily demonstrated that. Nobody's satisfactorily shown that you can solve unsolvable problems in, say, quantum chemistry by making a little analog quantum machine. I think there could be enormous opportunities there if people have the right ideas. This is where sort of the company called D-Wave plays, though there's a lot of criticism as to exactly what it is they're trying to do. And then the third part, which I think is particularly exciting for us at Argonne, and particularly I think at the CNM, is in quantum sensing, where we take advantage of the fact that a lot of these qubits have been developed, they have long coherence times, a lot is known, a lot of technology has caught up, measurement stuff. Can we use this development to, say, make detectors that use principles of, say, quantum entanglement to go below classical noise limits? Nobody has demonstrated this in a robust fashion, experimentally. If somebody can show that you can make a like a diffractometer or something that goes below the square root of n, classical noise limit, I think that's a huge thing. So I see a lot of opportunities there.
Peter. Our laboratory director should always have the last word.
This isn't the last word by any means. So you made a very interesting point about the fact that having a local source of power in a neuron allows you to have, fan-outs which are very large. So does that mean we have to start incorporating electrochemistry into thinking about devices? And is there a way that, I can feed circuits so that they're always kind of powered up throughout? Is there a plausible architecture for being able to do that?
So, this area requires a lot of thinking. I think the closest that we have that thinking in terms of this is using a flow cell battery. Right, where you use a metal with valence states that can be changed to do something like this. If you can transfer enough charge at the temperature that this thing is operating. But I think it is certainly possible to think of approaches such as those. Here, obviously, with the benefits of fan-out, because it's all ionic, you'll be trading speed. So this also has to come with an architecture. This is something we need to start working on and look into. Nobody is looking into it. But yes, I think that one can think of ways of using ions to do this. Ions and maybe charge defects inside a material.
Any final questions? Oh, please.
So I have always been fascinated by power being delivered remotely, and I've seen that in some science fiction movies. So how you've mentioned that in some of your slides. So how is that mechanism in physical science being done?
You mean the delivery of the power?
Remotely, yeah.
When I said power being delivered remotely in a silicon microelectronic system, it meant that I had a battery sitting outside the chip and it's sending power down a wire. In biological systems, the power is actually, I would say, delivered locally, like Peter said. There's a chemical bath, and by the motion of ions across a membrane, you set up an electrochemical potential difference that's called the Nernst potential, and then ions open up and you have a pulse that skims along. So that's not really remote power delivery, that's actually very local power delivery. Maybe I used the wrong term, remote meaning just a battery with wires going. Sorry.
All right, let's thank our speaker again.